Okay, so I'm hearing really a lot of good conversation right now. Thank you to those of you who took the time to go through that reflection sheet. You're going to find it beneficial to you during class today. Okay. Keep in mind, even if I don't check your homework for a grade, it doesn't mean it's not important. It's still very important. Okay. So on your reflection sheets, let's start with the basics. Okay. Pod 1. How do we get something to shift the graph left C units? Okay. And so pod 2, how do we shift it to the right? Okay. So inside of our function, if we add C, it's going to move it to the left. If we subtract C, it's going to move it to the right. Okay. That's kind of last year when you learned this the first time, that might have been kind of awkward for you that the plus made it go to the left and the minus made it go to the right. Okay. Anytime we have values inside of our function is affecting the x values. And anytime that happens, things are going to kind of counteract. So if you imagine like setting this equal to 0, x equals c is where we go to, and that's kind of why it's a shift to the right. If we set this to 0, x equals negative c, okay, that's a shift to the left. Okay. So you should be kind of used to that from last year because you've seen that before. But just remember, anything inside is going to kind of be backwards from what our eyes want to see. Okay. Pod 3, how do we shift up C units?
X, and then a C on the outside.
Okay, if we add it to the end, it'll shift it up C. And pod 4, how about down C? Okay, great. Anything on the outside of our function affects our y values. And so a vertical shift, we're going to have that plus c or minus c on the outside of our function, affecting our y values. Pod 6, how do we reflect about the x-axis? Okay, good. And pod, I skipped 5. I'm going to come back to you.
Add from negative x.
Okay. Okay. So here again, the negative's on the outside, so it's affecting those y values. So the y values go to negative. We're reflecting across the x-axis. Here, the negative's on the inside. Anything on the inside of our function affects our x values. So our x's are going to negative. We're reflecting about the y. Okay. Any questions on those? Those are the ones that were pretty quick to pick up on in yesterday's activity, correct? Those were the ones that you probably remembered the best, right? Maybe it took a little time to figure out which one of these was which, but the shifts you're probably the most comfortable with. Is that an accurate statement? Okay. Let's talk about the stretches. Okay? You are all doing a very good job of figuring out, oh, this was making it wider, this is making it skinnier. Okay, well, how do we describe those as stretches and shrinks? Okay? What you need to keep in mind is if we stretch a parabola horizontally, then it looks like we are shrinking it vertically. Do you see what I'm saying there? If we stretch a parabola horizontally, then it looks like we are shrinking it vertically. Okay. So, if we're going to stretch something vertically, how do we do that? Pod 7. How do we do that?
F of cx with c on the outside of parentheses where c is greater than 1.
Okay. So for a stretch or a shrink vertically, we want a c multiplied on the outside. Is that what you said?
Yes.
Okay. So remember, anything on the outside of our function affects vertically. So we're going to multiply on the outside. Okay? And you said c needs to be bigger than 1?
Yeah.
For a stretch. So c needs to be bigger than 1 for a stretch, and between 0 and 1 for a shrink is what Darby says. And do you agree with Darby? Okay, Darby is correct. Now, Ignore the fact that C could be negative because negative means reflection. We're talking about a C value aside from a reflection. Okay? So if I had a vertical stretch of C, how do we apply that to our parent function? Okay. So what would I do with all of my coordinates? First of all, is it affecting the X or the Y? It's affecting the Y value by a factor of C. So to apply this, all of our Y values get multiplied by C. So, I wrote it. Something like that. All right, let's talk about a horizontal stretch and shrink. Multiplying by C on the outside gave us a vertical stretch or shrink. So how do we get a horizontal stretch or shrink? I'm out of pods, so I'll have you help me out.
So F of C of F.
Okay, so we're going to multiply by C on the inside. Now, here's where we have to get. What? We flip them. So you're saying a stretch is now this. Is that what you mean by that? And a shrink is this. Okay, that is correct. Since a horizontal shrink and a vertical stretch look similar, their C values are going to have the same rule. They're going to be bigger than 1. Okay? Since a horizontal, I can't remember which one I said, but the other way around, like a horizontal stretch and a vertical shrink look similar, then their C rules look the same. Okay? Now, do you remember how everything was backwards when we applied it for our left and right shifts? Same thing's going to be true for your horizontal stretches and shrinks. To apply a horizontal stretches or shrink, we're going to take 1 over C times the X values.
Is that for specifically, like,
So since, it's just for these horizontal, so since horizontally it's affecting the X values, what's your question?
never mind. I was confused, but I got it now.
Are you sure?
Yeah.
Okay. Let me go to this square root graph over here. I'll write it on the board. This is our square root graph, right? So if we want y equals the square root of 2x, we have that C value on the inside. That's bigger than 1, so it's a horizontal shrink, right? And so horizontal shrink means like we're squishing this way horizontally. So instead of our coordinate being at 1, 1, our coordinate would be at 1/2, 1, because we have to multiply the x coordinate by the reciprocal of that number. That way we actually get the shrink to happen. Does that make sense?
Yeah.
Okay. It's very awkward. It's very awkward. Vertical stretches and shrinks are much more straightforward. And those are the ones you're going to see more often too. I'll admit that. Okay? So this is what we're going to do. We're going to do a couple examples, and then you're going to have time to work on your homework in class. And then, so lunch is going to be kind of weird because we're going to have some work time before and after lunch, maybe after lunch. And then we're going to talk about graphing piecewise functions, and you'll do a problem in class, and then I'll give you your first problem set of the class, okay? So, 2 examples and then work time. You'll notice over here on my board that I put up all of the functions from your chart. What I want you to notice about what I graphed up here is that I have 2 to 3 coordinates on each of them. Those are the coordinates I want you to focus on when you're shifting things. If I ask you to graph a parabola, you're not going to draw a U with a vertex. It's important that we have the correct shape. So those are the minimum points I need you to plot. You don't have to think, you don't have to plug any numbers in. You just need to know that that's their shape. Okay? What's the purpose of knowing all of these transformations? Okay, they're all the same. Okay? Why would I make you graph with transformations? Why would I make you do that? How did you used to graph? Right? Plugging X's to get Y's to figure out where your shape. That takes a long time. The purpose of these transformations is we can get a quick, clear graph and move on. Okay, this is for speed. Okay? Or where we're trying to make efficient use of your time. Okay? What? I will graph it and then erase it probably. No. Okay? So what is our parent function, Gabe? Okay, x squared. So I'm actually going to call it f of x since g of x has been shifted. Okay, so I'm going to call it a different name. All right, let's describe the transformations. Let's see. Jen, what is this x minus 1 doing?
It is moving it to the right.
So we have a shift right 1, and that minus 2. Molly, what is that doing?
Bringing it down 2.
Down 2. Okay? So here's what we're going to think of. What I do in green is not what I want you to write down unless you think you need to. I'm going to count. There's 1. So here's 1, 1, and negative 1, 1. Without really having to think, I know that this is the parent function. What we're going to do is we're going to shift it. I'm just going to use the vertex. We're going to shift right. Didn't write it down. We're going to shift right 1 and then down 2. There is my new vertex. I'm going to keep the same shape. So where I used to have the 1, 1 and 1, negative 1, boom. That red graph is what you would draw. How long did that take us? Like 30 seconds, but mainly because I kept talking. Okay? But what's important are those 3 points. Notice how I counted by halves, okay? But those 3 points are important because if we had some sort of stretch or shrink, those points would change, okay? In your book, it's going to ask you to write this in terms of f of x. You've already practiced doing that in your activity. You would write f of x minus 1 minus 2. The x minus 1 was inside of our function. The minus 2 was outside of our function. Okay? That's just describing the transformations in general. Second example. Ryan, what's our parent function? Excellent. So I'm going to draw it here. You don't need to, but it's just a reference for me. That's the coordinate 1, 1. Here's the square root of x. All right. So now we have some transformations. Okay. Will, what is this 2 doing?
Stretching it horizontally or vertically by 2.
So it's a vertical stretch by 2. I like it. It's on the outside, so it's vertical. It's bigger than 1, so it's a vertical stretch. Okay? That plus 3. Tannen, what's the plus 3 doing?
Left 3.
So we're going to shift left 3. This is my advice. Do the shifts last. Reflections and stretches / shrinks need to be done first. Okay? So since we're stretching vertically by 2, any y coordinate is going to get multiplied by 2. So instead of this being the coordinate 1, 1, it is going to stretch to be the coordinate 1, 2. That's our vertical stretch. Okay? Then we can take those 2 points and we can shift them left 3. And so there is our new graph. Okay? If it helps, you can lightly draw in anything you need to, as long as your answer is really dark or you go back and erase. I will do this just so you can see it, but don't feel like you need to. Okay? So, these are the homework problems that you're going to work on when you get back from lunch. My goal is so that you practice some of these before I give you your problem set this evening. Okay, and we can work together on these. So they're on your gold sheet. Okay, as you file back in from lunch, your book is out, you're working on these problems, and you're making really good use of your time, so that all you have to do tonight is your problem set instead of any of these problems. Okay, go to lunch, hustle back. Okay, so you've seen piecewise functions before. It's basically one function written with more than one equation, and each of those equations has a separate interval for the domain, so that the domains are not overlapping and it remains a function. So you have different pieces of different graphs put together for one graph. Raise your hand if you remember seeing something that looks like this before. Only one person's raising their hand. I know you've seen it. Okay. So basically, when x is less than or equal to 1, we have 2x plus 1. When x is between -1 and 1, we have 2x squared minus 1. When x is bigger than 1, we have 1 minus x squared. So you can see our domain is all real numbers, but depending on the domain, we have a different graph. So we're going to go through how to graph this one. And then you have the 2 problems from page 65. That's what they deal with, these piecewise functions. Okay. It's still written up there if you're still writing it down. Okay, so we're going to have 3 different pieces. At this point, it's fine to make an XY table, but do not feel like you have to. I'm going to make an XY table for each piece just so you can see how I get the numbers that I do. Okay? So what we can do is we can create an XY table for each piece. Our first piece is 2x plus 1. The domain for 2x plus 1 begins at -1 and gets bigger or smaller? Smaller. So I'm going to plug numbers that are small, begin at -1 and get smaller. Is -1 included or not included? It is included, which means we're going to have a closed circle at that point. So we're going to plug values in only to 2x plus 1. When we plug in -1, what do we get? -1. When we plug in -2, we get Okay, and we know that that is a line where x is less than or equal to 1. So I'm going to draw the piece of the line only for x is less than or equal to negative 1. Let's move on to our second piece. Our second piece is 2x squared minus 1. And that piece is defined between negative 1 and 1. So I can start at negative 1 and I can stop at 1. Now, some of you are saying, but negative 1 is not included. I know. We still have to begin there, but what are we going to put there? An open circle. Okay? And at 1 it's included, so we can put a closed circle. That's just a little reminder. You don't have to write that down. But when we plug in negative 1 to that second piece, we get 1. So we're going to put an open circle at negative 1, 1. When we plug in 0, we get negative 1. That can be a closed circle because we have a value there. And when we plug in 1, we get 1. And we have a closed circle because 1 is included. So there is that piece. And last but not least, we have the piece 1 minus x squared. That begins at x is 1 and gets bigger. Now I know that 1 is not included, which means we're going to put an open circle there, but we still have to begin there. So what happens when we plug in 1 to 1 minus x squared? So we have 1, 0, we have an open circle. When we plug in 2, we get 3. And we know that that is a parabola. That's going to keep going. Okay? So we have 3 pieces for one function. Notice how anytime we have an open circle, there's a closed circle, so it still passes the vertical line test. It is okay if an open circle and a closed circle overlap. Okay, because an open circle, technically, there's not a point there, so if a closed circle fills in that gap, that is fine. So the 2 problems on page 65, those are 2 piecewise function graphs to practice. Okay. So, here's the deal. You have a problem set to do for me. Okay? A problem set is a compilation of homework problems that you should have already done. So you're either copying them down, or what I would suggest, reworking them and making sure you're getting the answer you got before, as long as it's the right. Okay? I'm giving you 2 days to complete this. Okay? So my suggestion would be to make sure you finish at least the bolded problems from the 2 assignments for today. And then go back, there's 1, 2, there's 4 problems on this problem set. Okay? So you have 2 days to do 4 problems that you've already done. Bad, right? Okay, I'm giving you 2 days so that you can take your time and work on them nicely. And if you have questions, you have 2 days to come and ask me. I'm not going to ask questions about this in class on Thursday when they're due. You walk in here, you turn them into the basket. Now, there are some numbers on there, 4, 3, 2, 1, 4, 3, 2, 1. Do you see that? With each section, I've listed an objective that it's important for you to understand how to do for the test. So what I'd like you to do is, after you complete problem 10 on number 56, on page 56, I want you to evaluate your understanding of writing the domain and range using interval notation. Here's my scale. 4 is an expert. You could explain it to me. You could explain it to somebody else. 3, knowledgeable. I feel pretty good about it, but but probably not good enough to explain it to somebody else. Okay? 2, you're not really feeling that great about it. You kind of understand it, but not well enough. 1, you're a beginner. You kind of don't know what's going on for that, okay? So for each problem you do, you're going to evaluate yourself. How do you feel about that section? Okay? So make sure you read that sentence and evaluate yourself on the individual objectives. It is not bad to be a 1. Be honest with yourself. That just means we have some work to do. And if we do, then you and I both need to admit that. Okay? So, finish the bolded problems. You have this problem set to do, and when is it due? Thursday at the beginning of class. If it's not at the beginning of the class, it will be late. Make sure these are nice and neat and correct. Friday, our quiz reflections are due. And has anyone looked at the board and what the heck is going on Friday? Function aerobics. Transformation of functions is very important. We will be doing function aerobics on Friday, which means you need to dress comfortably because we are going to be moving the desks and we are going to be moving around the room like functions. It's going to be very exciting. I am going to wear a sweatband and bring Gatorade. Oh, sweet. It is going to be intense and fun. Okay? So, keep that in mind as you're practicing all of these functions and their transformations because you will get to be the functions on Friday.